So I'll begin with a word of prayer. Let's get up here. Dear Father, we thank you for this day. Again, I thank you for this class, and just ask you to help us use this time wisely today, just to wrap up any questions that remain about the course. Lord, in your name I pray, Lord Jesus. Amen. So this right here is a paper I wrote as in part because I work with some students on a problem of, I guess you could say, undergraduate research. And so like this paper I wrote basically is just an introduction to what I call acalculus. Acalculus is essentially just calculus where you replace real numbers with something else, something more abstract, like an abstract algebra. I would say this is not well known in the larger mathematical community. Here's a quote by some dude named Waterhouse. He says, "The theory has been developed only in fits and starts. In some sense, some of the simple results seem not to be on record at all, while others are only recorded in a language which is now hard to understand." This is what I found, is basically like this particular kind of mathematics has been discovered before, but it's not widely known, and it's unfortunate because it's actually very interesting. Essentially, let me get to the point here. In an algebra, that's an interesting one. If you have a partial derivative with respect to x1 through, xi1 through xik, and if you have a function which is differentiable with respect to this algebra, then in such an algebra, you're able to trade this partial derivative for this multiplication of algebra elements. So there's like this really neat relation between the differential calculus of the algebra and the multiplication of the algebra. And so like I've basically worked out calculus 1, 2, and 3 with some students. So like all of the basic theorems and stuff are known. Let me, like here, but the trouble is, of course, in terms of discussing this with other people, is like there's this like multiplication of terminology which happens. Like this table, these are all names for the same set of numbers. Now I will usually call these things hyperbolic numbers. They're sort of like complex numbers, except instead of having I squared equals to -1, you have j squared equals to 1. I'll show you in the next 10 minutes or so how we can use hyperbolic numbers to derive the D'Alembert solution to the wave equation. But before I do that, I should tell you a little bit about what we mean by calculus on a normed linear space. Like basically, the idea is the same as usual. Essentially, the idea is that there's a derivative, which is this term, and the difference in the function at nearby points can be approximated by the derivative such that it's basically arbitrarily close. So it's the best linear approximation to the function. That's what the derivative is. And in an algebra, what's an algebra? An algebra is just basically a space where you can add, and you've got this multiplication which satisfies a distribution, like the regular distributivity rules. It's like associative. I only look at associative algebras. And there's like a number 1 in the algebra that behaves like the number 1. And I usually, for the most part, look at commutative algebras where multiplication can multiply in either way. It turns out that to understand the algebra, you can instead trade it for understanding matrices which represent the algebra. So I'll get to that here. So basically, this is called the regular representation of the algebra, and I have a few of them to look at here once I get to it. Come on, where's my list? Examples, yes. So of course, real numbers are an algebra. Complex numbers, we've worked with those. We couldn't help but do that this semester, right? And complex numbers correspond uniquely to these 2x2 matrices of the form A minus BBA. This is almost the real Jordan form. We saw this almost this kind of matrix when we solved like the complex eigenvector problem, right? It's very close to that. Hyperbolic numbers, in the same sense, correspond to matrices of the form ABBA, right? And hyperbolic numbers are really cool. Like I said, they're like complex numbers, except the reciprocal works like this. There's also like a hyperbolic conjugate. And when you multiply this top and bottom by a minus bj, you end up with a minus bj upstairs. But you end up with a squared minus b squared downstairs because j squared is 1. So like the reciprocal of a hyperbolic number only exists in as much as this denominator is non-zero, right? So there's tons of non-zero hyperbolic numbers which nevertheless do not have multiplicative inverses. Hyperbolic numbers are not what's called a field. So what that means is that there's weird stuff in there. In particular, there are these zero divisors, things that multiply to zero and yet are not zero. So because of this, it turns out that there is a nice, like what's called isomorphism, which is fancy words for a better notation for hyperbolic numbers in some sense. And so if we just look at R2, another way you can multiply vectors in the plane, and some of you have done this in like Calc 3, it's a very popular mistake. I ask you guys to calculate the dot product of two vectors, and you give me back a vector, right? If you do that, you're going to do it like this, right? A times C, AC, B times D, BD, and you're like, the dot product of this vector and this vector is this vector. Well, what you didn't know is you're actually giving me what's called the Hadamard product of the vectors, right? So I sometimes joke with other professors that the students aren't wrong, they're just more sophisticated, you know? Like, because they just not giving me dot product as a number because they know better. They know the Hadamard product, but this is, of course, a joke with a very limited audience, which is not including this one. And so anyway, there's these isomorphisms that this goes from the Hadamard product over to the hyperbolic numbers or vice versa. So there's these isomorphisms, these product preserving maps from one thing to the other. I'm only mentioning this in as much as we need it in order to derive the D'Alembert solution. But you can do other cool stuff, like if you want to solve the quadratic equation, for instance, in the hyperbolic numbers, you can trade it for a pair of quadratic equations in the Hadamard product, and that ends up giving you just a regular pair of quadratic equations. How many solutions are there to a pair of quadratic equations like this? Well, each one of these separately can have as many as two distinct solutions, right? So if you do the counting, you've got up to 4 solutions, right? Or it could be that one of these is a repeated solution and one of these has distinct solutions. That gives you 2 total solutions to your quadratic equation. Or it could be that both of these are like, you know, no solution ones. They're both irreducible in the real sense, in which case your hyperbolic quadratic equation would have no solution. So a quadratic equation in the hyperbolic number has as few as none, as many as just one. All right, it could be that you have the same solution repeated both places, and the other possibility, of course, is you either have none, 2, or 4 distinct solutions for a quadratic equation over the hyperbolic numbers. That's kind of weird, right? If you study quaternions are like, you know, it's a 4-dimensional space with I, J, K, and a real quantity. These predated vectors. The people used quaternions to model science and engineering for about 50 years before the vector formalism came to rise. That's why we use I hat, J hat, K hat in like the typical calculus books. That's in honor of the quaternions of Hamilton, which used I, J, and K. But the quaternions have I squared is equal to J squared is equal to K squared is equal to -1. It's kind of like 3 copies of the complex numbers hobbled together in a very particular way. If you study a quadratic equation in the quaternions, there could be infinitely many solutions to a quaternionic quadratic equation. So quadratic equations over algebras other than the real numbers or the complex numbers pose interesting questions, actually. So that's one of the kind of low-level questions I have sitting around for students. If they're interested in research with me, they could just study the quadratic equation in one of these algebras and see what they find. It's not easy, necessarily. There are also dual numbers. Dual numbers, in some sense, like model infinitesimal calculus, because a dual number has the form a plus b epsilon, where the epsilon squares to 0. So the epsilon's kind of like an infinitesimal, right? So you can model formal calculus with these dual numbers. There's also nth order dual numbers where epsilon to the n power is 0, but epsilon to the less than n power is non-zero. The matrix for dual numbers like this, the matrix for n dual numbers like that. These ones I'm especially fond of. These are the 3 hyperbolic numbers. These are ones of the form a plus bj plus cj squared, where j cubed is 1, all right? The matrix representation of these look like that, all right? And there's other things that you can do. So I'm just trying to give you a flavor for this. These are the matrices of the 4 hyperbolic numbers. And you can take like pairs of hyperbolic numbers. You get matrix representations that look like this. For the likewise for the pairs of complex numbers. Now, this is the matrix of the quaternions right there. Now, so how do you define differentiability over those different sorts of algebras? Well, you define it in terms of what's called real differentiability. In other words, that the change in the function can be approximated by basically a matrix times a vector, which is the matrix is called the Jacobian matrix. If that's possible, it's real differentiable. And to say that the mapping is adifferentiable means that the differential has a very particular property. It allows you to factor out the multiplication by the algebra. It turns out what this means is that the matrix of the differential, which is what we call the Jacobian matrix, which you could calculate easily. The Jacobian matrix is just like the partial derivatives of the function put in columns. Like the first column is x1 derivative, the second column is the x2 derivative, the nth column is the xn derivative, right? So adifferentiability simply becomes the statement that the Jacobian matrix has to have the same shape as one of those matrices I was just showing you. Adifferentiability of a function means that its Jacobian matrix is in the regular representation of the algebra. That leads us to what are called the Cauchy-Riemann equations. So if you take complex analysis here, we'll study the Cauchy-Riemann equations. There's just 2 of them for complex analysis. But for an algebra, there's generally n squared minus n of them. And so what I'm scrolling past at the moment is just the fact that calculus works the same for differentiation over an algebra variable as it does in the real case. There's a product rule, there's a chain rule, all that jazz. If you had for example, here's the nth power in the algebra, zeta to the n. Well, the derivative of the zeta to the n function is n times zeta to the n minus 1. No shock there, right? So power rule still works. You can define sine, cosine, exponential, all of your favorite elementary functions we can define by their power series over the algebra, just the same. Let me get it to here. It's here's some Cauchy-Riemann equations eventually. Sorry, I'm trying to find it. So let me just skip ahead here, as I don't want to take all class with this. Anyway, there's a lot more to learn here, obviously. I have tried to teach this material alongside complex analysis, but I don't do it anymore because the semester I tried to do it, it kind of broke the brains of the students in the class, and they were pretty good students, and I was like, all right, I guess I can't do this. So I just teach complex analysis when I teach complex analysis. So I really need a course past complex analysis to teach this properly in a course. We don't have such a course. So it's really just left to students who are interested and want to research with me to study these things if they're so inclined. But, okay, so here's those 3 hyperbolic numbers I was talking about before. And if you had a function which is differentiable with respect to the 3 hyperbolic numbers, it's automatically the case that you have the xx derivative is equal to the yz derivative, the xy derivative is equal to zz, the xz derivative is equal to the yy. Because if you look at the multiplication table of 1j and j squared, notice that 1 times the 2 is equal to the 2, 1 times the 2 is equal to the, let's see here, the 2 times the 2, right? So that would be something like the zz is equal to the 1, 2, fxy. So whatever patterns there are in the multiplication table, there's also the same, you can match up the same matching partial derivatives. Let's see here, j squared. So the z, this would be the xz derivative, this would be the yy derivative. So xz, yy, right? So there's this, you can translate from the algebra to the derivatives. In complex analysis, you have I squared equal to minus 1, right? This is the multiplication table for 1 and I, Notice that 1 times 1 is 1, but the second thing times the second thing is minus 1, right? That means that whatever's here has to be equal to minus whatever's there in the matching table for second derivatives. So for complex variable function, if you have fxx and you have fyy, it has to be the case that fxx is equal to minus fyy. But what does that mean? Well, that means that fxx plus fyy is equal to 0. You guys should recognize that. You were just working on that. That's Laplace's equation for f. So what I'm telling you is if a function is complex differentiable, it automatically solves Laplace's equation. Laplace's equation being the xx derivative plus the yy derivative being 0. This is why when we study complex analysis here, you will find a new toolkit full of ways to solve Laplace's equations that are well beyond this course. There's something called conformal mapping, which allows us to solve a vast array of Laplace equations. Incidentally, I have an existing project on trying to modify the method of conformal mapping to other algebras in some kind of meaningful way. I have not solved it yet in a way which I like. I've had a couple different students try it. Nobody's cracked it. Not really. Well, anyway. So here is the wave equation, right? C squared uxx is equal to utt. So if we want to solve the wave equation, one thing we can do is convert the differential equation to an algebra equation. And so I'm saying if I want c squared uxx to be utt, that in the algebra makes me think I want a c squared is equal to k squared, where the k is the algebra element and c is just a given constant, the speed of the wave that we're interested in. So this makes me think of looking at an algebra of the form WC, where it's the reals plus k times another copy of the reals, where this algebra element k has k squared equals to c squared. I can make an isomorphism from such a space to the hyperbolic numbers by this. I just do x plus kt maps to x plus cjt. That gives me an isomorphism, and then I can compose that with the other isomorphism I talked about earlier to get an isomorphism that goes from the space I've just created, this WC, to the plane with the Hadamard product. And hey, come on. Man, that's lame. My son let me borrow his laser, but didn't tell me it was the laser's got no staying power. No worries. I have a laser myself. So if I can make an isomorphism from the direct product algebra from my WC space to the direct product algebra, and the isomorphism is just this. All right, x plus kt maps to x plus ct, x minus ct. But then the thing is, when you study differentiability on the Hadamard product, it's very simple. Like a function's differentiable in the plane only if the first function is just a function of x and the second function is just a function of y. It's kind of silly the way that such functions are differentiable. But then I have a theorem in this paper which basically says that I can transfer differentiability from one algebra to an isomorphic copy of the algebra, which tells me that any function that is WC differentiable corresponds to an RR differentiable function through composition with this isomorphism, like this. But what that means is that I can construct f like so, but remember that any function on the direct product algebra is just a pair of functions of just the first thing and just the second thing. It gives me like this, which when I pass through the representative formulas, I get this. But this, my friends, is exactly the D'Alembert solution when you just look at it. I get this for u, and I get that for v. This is, well, it's a superposition, I suppose, but I mean, these are the left moving waves, and these are the right moving waves of the D'Alembert solution. So, in other words, this A calculus gives me a way of deriving the D'Alembert solution simply from the underlying algebra corresponding to the differential equation. So this is kind of like, in a nutshell, one of my bigger goals in this research is to, for any given partial differential equation, if I can, I'd love to find a corresponding algebra which the very structure of that algebra naturally reproduces the kind of functions we see in the differential equation, and perhaps gives me additional insight. Anyway, so that's kind of just a a really brief overview of, and the thing that's interesting about this, perhaps, maybe not so much, is after that, I did another paper with a student, Nathan Bedell. We wrote this Introduction to the Theory of AODEs paper, and in this paper, basically what I show is that everything we do in this course, the nth order stuff, the systems, okay, not the Laplace, I haven't done that yet, but a good chunk of this course can all be done over an arbitrary associative algebra. And like we actually have a method to solve the constant coefficient problem over an arbitrary algebra in this, the Wronski and all that jazz, it all generalizes. So, I don't know, I still haven't published this paper somehow, but oh well, maybe someday. I sent it to a journal and they sat on it for like a year, and then they're like, well, we don't have anybody that can you know, whatchamacallit, review it. It's outside our scope. I'm like, oh, great, thanks. And then I got busy. And then that student graduated and it became less important to publish it. So here it is. But anyway. All right, so that's, I just wanted to tell you guys a little bit about that. Now that I've got that off my chest, do you guys got questions about this course?
How many questions are going to be on the final?
How many questions are going to be on the final? Always a popular question that I will never answer because it doesn't mean anything. I mean, the final is usually like 7 to 10 pages, somewhere in there, you know. Let's see here.
7 to 10 pages?
7 to 10. It's 2 hours of work, so it'll take you 2 hours. I try to cover everything.
Will we be allowed a note sheet?
I think I have said you're allowed 2 pages of notes, front and back. So that's like 4 pages of writing.
What kind of problems do you suggest that, are there any problems that are like all encompassing that have a lot of different ways of solving?
Well, I don't know, like, I think if you go back to the start of this course, right, and you go back and you look at test 1, I don't think we ever really learned anything that supplanted these methods, you know? Maybe with the sole exception of, there's one kind of problem that I like to solve a different way than we did originally. So like this thing, right? If I have y prime, oh man, yeah. If I have, you know, y prime minus 3y equals e to the t, right? We solved that with the integrating factor method before. If I see that on the final, personally, my way is to do this. Oh, so y is equal to c1 e to the 3t plus a e to the t. But yp is a e to the t. So yp prime minus 3yp is equal to 4a e to the t, which is equal to e to the t. Therefore, a is equal to 1/4. And so my solution is c1 e to the 3t plus 1/4 e to the t, right? Like that surely is easier than actually doing integrating factor method. Yeah? So in as much as, if you have a constant coefficient problem, and it happens to be first order, I mean, I use the, you know, annihilator method stuff, basically. But that's the only thing I can really think of that we found a better way later to solve, yeah? I'll tell you what I would not do is like try Laplace transforms. Although you could solve this with Laplace transforms, right? You could, but I don't think that's the best way. So let's see here. How many of you guys lost points because you didn't put minus there? Many of you lost those points. As does every year of differential equations when I ask this question every single year. I tell people I'm going to do this, and I do it, and people still get it wrong. But when we're taking a square root, we have to allow for plus or minus. If we have a negative initial condition, you need a minus probably, right? I can't get y of 1 is minus 2 if I put a plus here, right? And you can't put plus or minus here. I don't allow you to just choose all possibilities. Like, you got to pick, all right? So we're looking for a specific solution here. Anyway, that's easy enough not to get wrong. Let's see here. Constant coefficient problems, of course, still matter. The spring mass, this caught a lot of you guys off guard, but there was no need for that. This one's not hard. Yeah, you can do this. You can do this. Let's see here. The integral curve problem, we've looked at it two different, really different ways, right? The one is to find the Cartesian equation of the integral curve, right? More recently, we've looked at the parametric equations of the integral curve, right? So those are really different. Could I ask you to find the parametric equations for this integral curve? I don't think I could. Why would that be? I mean, I could, but I think it would be at least rude, perhaps improper. To find parametric equations for this one, I would be up against dy dt, my bad, dx dt. Let me turn the lights on in here. Come on, there we go. Dx dt is minus 3y squared. And dy dt, I would need to solve 5x to the fourth, right? Do you remember when we solved systems of equations like this? You shouldn't, because we didn't, right? What kind of systems of equations did we learn how to solve in here? What was our first step in solving a system every time? We had what, like x prime, y prime, z prime, whatever, equals to what? 3x plus y minus z, 2y plus z, x minus z, right? The point was we could organize those into a what? A matrix, because they were linear, right? So like this one that I just wrote up there in the blue is not linear, which means that I can't just go, oh, I know how to solve any linear differential equations. We use the matrix exponential, we use eigenvectors, generalized eigenvectors, it's all there, right? There is no such universal hammer you can hit everything over the head with when it's nonlinear. Like this kind of thing, I don't know. I mean, I probably can solve it. They're relatively simple, but it's anybody's guess if I can find parametric solutions to that. That said, this little trick where we take the quotient of q over p to look for Cartesian curves which are integral to the vector field, that eliminates the subtlety, and we're just up against a dy dx equals to stuff equation, right? Which is, we can solve all kinds of nonlinear ones of those, as we saw at the start, right? So the first order problem is much more forgiving in the sense that we can solve a bunch of nonlinear first order problems by separation of variables like here, right? And we got other tips and tricks. This was essentially a homework problem. I mean, it's kind of a twist, but remember, if for this to be exact, we need that what? We need that the closed condition holds, right? We need the y derivative of this to be equal to the x derivative of that in order for this to be exact. And that puts rather strict conditions on what a and b have to be in order to make that happen. So there's that. Don't forget, like, to setting up the particular solution, there's a lot of things to think through there. There's a difference between setting up the particular solution versus actually finding it, right? Setting it up is just the starting point. After that, you have to do what? Plug it in and work out the algebra to see what the unknown coefficients actually are. Unless it says explicitly not to, right? In which case you better not do it, because you're wasting precious time if you're finding it when you've not been asked to, right? So do be careful to read the instructions, Let's see if I can find one which is more like that. well, I'll get back to that in a second here. Something like y prime plus y equals the secant cubed, you should immediately recognize, oh, this is not undetermined coefficients. If you see a secant or a tangent, you're in variation of parameters land, right? You need to use the variation of parameters formula. That's how that goes. Which means you need to integrate. So, some of you are pretty weak on integration. You would do well to write down a list of 20 basic integrals to check yourself on. You know, I'm just saying. Be careful with the integration. This is the Cauchy-Euler problem. Of course, there we basically guess y equals x to the r, and it gives us a characteristic equation like we see here. You know, turns out we have 1/2 and 1/3, which gives me the solution. This one, I end up with 1/2 plus or minus 3i, and remember that when that happens, we get a x to the 1/2, which is square root of x, but then the cosine, e to the ix, we have to remember there's a little bit of something there. So like e to the I beta x, right? It works out to cosine beta x plus, I'm an idiot. We had x to the I beta x though, right? Excuse me, we had x to, I'll get it eventually. We had x to the I beta, right? X to the I beta gives us, as it turns out, the natural log of the cosine of beta x. Wait a minute, I still got it wrong. Oh, goodness gracious. So sad. Cosine of the beta times the natural log of x plus I times the sine of beta times the natural log of x. There we go. That's what I'm supposed to do here. You guys got formula sheets, so you don't have to remember these kinds of things, but if you were so inclined to learn these sorts of things, here's how I think about. I have x to the I beta, and what I do is I trade that for basically e to the natural log of I beta. Well, excuse me, e to the natural log of x to the I beta, which is technically speaking nonsense, but don't tell the other math professors, it'll be fine. And then so we have e to this is just a heuristic, okay guys? E to the natural log of x times e to the I beta natural log of x, which then of course gives me cosine of beta log x plus I times the sine of beta log x. Now if you go back and look at what I did in the notes and stuff, I basically just gave you this as a definition there. So the definition of e to the I beta is this. Right. Now there's a real and an imaginary solution there, right? And so we use the real part for the first part of our solution and then the imaginary part for the other part, right? That's how that goes. There should not be an I in the solution, right? We want the real solution. I don't expect you guys to know substitutions. So if there is a substitution which I think is needed, I will probably suggest it, much like this problem, right? Here's a Bernoulli equation. I'm like, make a w equals 1 over y cubed substitution, and good things will happen to you, right? And indeed, good things happen to us. We solved it. Woohoo! There we go. Here's what I was talking about a second ago, but I've kind of safeguarded you in this problem 12. See, sometimes in the past I've given this problem like, suppose you've got d to the 4th plus 9d squared acting on y equal to x plus cosine x. Then I'll say, set up, but do not find the coefficients a, b, c, d. Right? This is how I used to ask this question, but I realized that if I ask it in multiple choice format, then people are less likely to just actually try to find yp. And mostly it works, but so anyway, this one we annihilate the right hand side by, I think the x needs a d squared and the cosine needs a d squared plus 1. So if I multiply by d squared times d squared plus 1 both sides, I get 0 from this. And it leaves me that, which of course then gives me a d to the 4th and a d squared plus 1 and d squared plus 9, which gives me this ginormous general solution. But some of this we don't need, right? Because this piece and that piece are part of the homogeneous solution for the original problem, which means whatever is left over, that's my correct form for the particular solution, which happens to match with part C here in this test. So anyway, I can keep going through here. For the if you have the force which is given as a function of velocity, and I ask you to find the velocity as a function of position, it's important to know about the m times acceleration can be rewritten as m times v dv dx, because that eliminates time at the level of calculus, and then we can just separate variables and solve for v as a function of x, right? The other path would be to find v as a function of t, and then integrate again, find x as a function of t, solve that for t, and then plug t as a function of x back into your v of t to find v as a function. I don't recommend this. This is a bad way, all right? You would much rather eliminate t at the level of calculus right here so we can straight away get to the kind of answer we're looking for. But that's a trick. You should remember this v dv dx trick. Otherwise, it's hard to do that problem. But of course, that was in the homework, and we did work problems like that in class, I do believe. Let's see here. What happened next? I think we went to test 2, right? There was only a test 2, wasn't there? Where were we? So, all right. So, another thing to think about for your formula sheet, if you don't have a clear and commanding understanding of the power series expansions for sine, exponential, the geometric series, the standard examples from Calculus 2, if you do not know these, you need to put those on your formula sheet so that you can use them. Because the first step of finding a series solution to a differential equation is converting anything that's not given as a power series into a power series. So like sine of x is nothing more than x minus 1/6 x cubed plus dot 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 dot. That's the Maclaurin expansion for sine. And the other thing that you guys need to pay more attention to, some of you, not all of you, but some of you, is that when I give you initial conditions, and that's super nice for the power series solution, because I'm telling you that the first term is 4 and that the second term is 7, right? This 4 plus 7x, that's basically the tangent line part of the power series, which is given by this initial position, initial velocity, or initial slope, if you like. So I know the 4 and the 7 just from Taylor's theorem to start with, right? We've all had Calculus 2. We know Taylor's theorem. Okay, so then I differentiate it again, and then I'm looking for, like, what's the arbitrary terms? I plug it in, and then I simply equate coefficients of the constant terms, the linear terms, the quadratic terms. So constant level, I've got 2c2 equal to 0, all right? At which point I was like, oh, drat, because I asked for 4 non-zero answers, right? So at this point I had to go back in the solution and add a term here and here and here, full disclosure, right? Because like I thought maybe I could get away with just writing this much, but then after I got to this 2c2 equal to 0, I realized I needed to get all the way to like c4 in order to get 4 non-zero things, you know? Because 0, 1, 2, 3, that would be 4 things. But if 2 is gone in terms of non-trivial, then I have to go all the way to 4 to get 4. For x, the x I've got 6c3 here, and then like over here, the only way to get an x is from this x times 4. So that gives me plus 4. And so that gets me c3 is 2/3 minus 2/3. And then for x squared, I get the next term here that I haven't written is this 12c4x squared. And then over here, the only way to get x squared is from like x times 7x, which gives me a 7. Notice that everything else is cubic or higher order. So the only way to get x squared is from this x times that 7 in this mess. And so lo and behold, I get c4 is minus 7/12, which then putting it all together gives me this. So some of you got this, but many of you did not. And there's no need for that. You guys can get this problem, you know? You can do this. Not a big deal. Here we have a case-by-defined function. So like first order of business is to convert it to, like the unit step notation. At least that's how I do it. Other professors might be teaching like to integrate from the definition. I don't know why you do that. I don't think that's the best way to calculate by any means. So anyway, this is just a standard thing. I e to the t, I turn it on at time 0, I turn it off at time 1. Sine t, I turn on at time 1, I turn off at time pi. Regrouping, I have e to the t ut, the difference of sine and exponential times the unit step function t minus 1, and then of course this lonely minus sine t u of t minus pi. Once I have that, I have to take the Laplace transform of each one of these pieces separately. E to the t times ut, that essentially this ut, you can just ignore it. If you got u of t, it doesn't matter. So basically just ignore it. That gives you 1 over s minus 1. This piece here, we have a ut minus 1. That gives me e to the minus s. Then I have to take the Laplace transform of the function multiplying it. The rule is we take the t and replace it by t plus 1. So I have sine of t plus 1. I've got e to the t plus 1. Over here, I have e to the minus pi s because it's t minus pi. And I have to replace t with t plus pi. Then I have to do algebra. Algebra says sine of t plus 1 is cosine 1 sine t plus sine 1 cosine t. And this is minus e to the t. And then over here you got sine t, because when you do adding angles formula for this guy, you get, sine t cosine pi plus cosine t sine pi. Sine pi is 0, cosine pi is minus 1. That's why this minus changed to a plus. Right there, there's a cosine pi that I used to make that minus become a plus. Then we know the Laplace transform of this, and that. They're all in the sheet, and there they are. Cosine 1 over s squared plus 1, s times the sine of 1 over s squared plus 1, because the Laplace transform of cosine is s over s squared plus 1. And then this e to the t transforms to 1 over s minus 1. And then over here, and there it is. So many of you got this wrong. Needlessly so. We can all do this. This is part of the course. You're expected to do this. People who pass this course can do this. There are some people who don't pass the course, who don't do this, who still pass the course. That's true, but just do it. I want everyone to pass with a wide margin. Leave a lot of distance between the 70 and your score, please. I do replace test 1 and test 2, if helpful, with the final exam score. So anything is still possible, right? This one here, what's going on is we've got a complex eigenvector with eigenvalue 1 plus 3i. And then over here, we've got a generalized eigenvector of order 2 that, v4 is an eigenvector with eigenvalue 0, but v3 is a generalized eigenvector of order 2, again with eigenvalue 0. So for the complex eigenvalue, remember it goes like cosine of the, so we have an e to the t from the 1, and we've got sines and cosines of 3t from the 3i. And then I've got the real part of the eigenvector minus sine times the imaginary part of the eigenvector, and then here's sine times the real part of the eigenvector plus cosine times the imaginary part of the eigenvector. It would be smart to write down the formula for how we write down the real and the imaginary solutions for a complex eigenvector on your formula sheet, right? Because this is something that's very, very likely to come up on the final. If not symbolically like this, then certainly in the 2x2 case, right? I almost always test on that. Indeed, it was tested on down here, as we'll get to. Now over here, the reason that these terms appear is because when we, e to the 0t is just 1. So this one, I hope you guys understand, but let me write down a little bit more. So remember how it goes. We have e to the lambda t u, 1 for an eigenvector, and we have e to the lambda t times u2 plus tu1. This is for a minus lambda I, u1 equals to 0, and this is for a minus lambda I, u2 equal to u1. That implies that this, is solution. This is a solution. And we take a linear combination of those guys, and that gets us the general solution, yeah? So that's what's going on here. But the thing is, e to the 0t is just 1. So that's why I have this term and that term. This is the eigensolution, and this is the generalized eigensolution, all right? So that was part B. Yeah. You guys can jump in and ask a question if you got it. Otherwise, I'll just keep blathering. The 2x2 problem. This is a complex eigenvalue, as I was saying. I would encourage you, if you don't know the completing the square yet, take some time to learn it. It's worth it, right? We multiply it out. We take half of the coefficient of this, whatever it is, in this case 2. Lambda minus 2, that's squared, right? Now, if you think about that, there's a 4 hidden in this that wasn't up here, so I have to subtract 4 from 13, which gives me 9. And that's completing the square. Now, once I've done that, I can read from this immediately that my eigenvalues are 2 plus or minus the square root of 9, which is 3i. So, yeah. Now, then I have to find the eigenvectors, right? So I have a minus lambda I times uv, which is this, which is that. And so basically these are the same equations, but I'll just look at the second one because I like it. It's kind of pretty. Relatively speaking, prettier. I don't know. It's kind of about the same, whatever. You could have gone with the top equation. Some of you did. That's fine. There's all like, okay, so essentially the point here is to find the complex eigenvector. I usually end up choosing a particular number for u or v. In the complex case, you could just as well choose u or v as like any complex number instead of 6. I could make that essentially like 17 plus 3i, and if I did that, it would make my eigenvector look totally different. But I think it would still work. So it's kind of obnoxious in that regard for me as a grader. But you just make a choice. I recommend a choice that kills fractions. That's why I put 6 here, because then I don't have sixths in my answer, you know. So I've got 3 plus I over 6 because I chose v equals to 6, and that makes u 3 plus I. So I put that in. And so that's the real part of my complex eigenvector. That's the imaginary part of my complex eigenvector. And then when I look at this, this is my complex solution. I'm going to have, you know, cosine times that minus sine times that is the real part. You don't have to work through this in your solution. You can simply write down the boxed equation as the solution. I wouldn't take points off. I'm just explaining in my solution, all right? Like, I'm totally fine with you going straight from here to there immediately, like just like that. Like, you don't have to write this down here if you don't want to. You can go straight from here to here. Totally fine. That's what the book does. So we've got, you know, cosine 3, 6 minus sine t 1, 0 plus, you know, the sine t 3, 6 cosine 1, 0. And of course, they both have to be multiplied by the e to the 2t, which is coming from the 2 and the real part of the solution. So that was that. This one is another multiple choice. And this time I gave you a 3-chain, I believe, the eigenvector v1 with eigenvalue 2. And then notice that v2 maps back to v1. And so that makes v1 and v2 a 2-chain with eigenvalue 2. v3 is over here on its lonesome. It's got nothing to do with 1 and 2. And it's just an eigenvector with eigenvalue 2. So I expect then I have 2 eigensolutions and 1 generalized eigensolution, like the order 2 kind, like we saw in the other problem. So I think that's given by part A here. C1 e to the 2t v1, my eigensolution. C3 e to the 2t v3, my other eigensolution. And then this in the middle, we get from the magic formula, concatenating if we put lambda equal to 2. That's the kind of solution that comes from that. So, which I kind of show down here, you know. But as a general rule of order, I do not give partial credit for the multiple choice questions. So, you know, just so you know. Let's see here, this one, again, 2 by 2, write down the characteristic equation, ends up being lambda minus 7 squared. So I get my eigenvector, like so. Then I have to find a generalized eigenvector of order 2, like so, which gives me this. And then I use the magic formula to get my second solution. If you're seeing how things work here, you notice that if you really understand what's going on, you don't really technically need to write out the magic formula and derive this every time. I'm perfectly fine with you not writing all of this out and just going straight to, since this is a generalized, you know, eigenvector of order 2, which satisfies the chain condition, this is the general solution. Like, you can go straight from there to there. We've done this enough times that I think that's not an unreasonable jump. But there you go. That's the general solution. Notice that it's not just t times the vector, right? We actually have to think through this business up here. Now, if you haven't thought through it, then you need to go through it, you know. But if you do understand, it's just always this. It's e to the ta times v2 simplifies to e to the 7t times the generalized eigenvector of order 2 plus t times the eigenvector, which is below it on the chain. So, all right. This one here, I think, is a nastier problem. All right, this one's, I think, personally, I feel like this is a more difficult problem because, in part, because it's got this, you know, cosine 3t times 7t, which somehow or another you need to rewrite as 1/2 cosine 10t plus cosine 4t. So if you have the requisite trig identities on your sheet, great, you can use them. Otherwise, I like this as a method of derivation, but whatever. So once you do all that, we've got t times this business right here. And then there's a theorem which says that, hey, that's minus the s derivative of the Laplace transform of these two guys, which is this and that, which is this, which is that. So great. I think there's a lot of you who like got this, who didn't get the earlier Laplace problem right, which is kind of weird to me. This is, I think, a more difficult problem than the problem way back here. Like this is entry level. Everyone should get this one. I don't know, maybe this is harder. I guess it's hard. You know, it's harder. It's harder because it's got this pesky, like, you have to evaluate the function at t plus 1 business, right? Or t plus pi. Why are there so many fruit flies in here? Like, my laser was just, like, making them, like, jump off the screen. That was weird. But anyway. Sorry, I'm easily distracted, as you know. Whoa. I think I went too far. All right. This here, find the general solution of this differential equation. It's the 3x3. As I told you guys, if I give you a 3x3 problem, it's going to have something nice about it. Like either 0 is going to be an eigenvalue. If 0 is an eigenvalue, that means when you calculate the characteristic equation, lambda factors out. So you're just left with lambda times the quadratic. We can factor any quadratic, so those aren't too mean. But in the wild, then this actually was one of those. So, but I was more generous here. I told you that there are two interesting vectors. So the question is, what does that mean? What can it possibly mean? So pretty much there's really only one thing to do here, which is to multiply the matrix by the vector and see that, oh, I've got an eigenvector with eigenvalue 0. And, oh, I've got an eigenvector with eigenvalue 3. So you're like, this is how I test matrix multiplication, if you're wondering, right? I didn't have a, hey, multiply the matrix question like I have in the past sometimes. So I just let matrix multiplication come up in the context of other problems like this one. But anyway, the characteristic equation, after some math, works out to this. And that's not surprising because we knew 0 and 3 were eigenvalues. So of course they're there. And what's left is this lambda plus 1. Which means I need to go look for an eigenvector with eigenvalue minus 1, which I can do. And that gives us this, right? Which, if you look at it, the first equation and the last equation are the same one. And well, when I looked at this before, I could immediately see that v was 0. I'm not sure how I saw that at that point, but anyway, v is 0 apparently. And once you know that, if you put that into either the first or the second or the third equation, you end up with u is equal to minus w, which puts us in the world of something like minus 1, 0, 1 for our eigenvector. And there we go. Then we write down the general solution, e to the eigenvalue, which is e to the 0 times t, which is 1. 1, 1, 1, plus c2 e to the 3t times that, plus c3 e to the minus t times that. And there you go. Even if you couldn't find the eigenvector with eigenvalue minus 1 here, you ought to have been able to write down 2/3 of the solution just from what was given, right? I gave you two eigenvectors. Each one gives you a solution. You could write these down even before you calculated that, right? You should have been able to get, you know, half credit or something for that, yeah? This here, you guys got to be careful not to, so I think some of you are not being careful about the distinction between delta and u. Delta is the Dirac delta function, u is the unit step function. These are very different things. Get out of here. Anyway, sorry. So I take the Laplace. Oh, wait a minute, it's up there. All right, now stop. I take the Laplace transform of this. The Laplace transform of the Dirac delta was just e to the minus pi s as we worked out. Now, this gives me s squared. Why is there a 2 here? Because there's a 2 here. Why is there a 3 here? Because there's a 3 here, right? So minus s times y of 0 minus y prime of 0. plus 6 minus 6. It has to multiply everything that Laplace transforms from y prime, namely 6 times big Y and the minus 2. So that multiplies to give me a minus 12. Somebody missed that. It's not too big a deal, but it will change things. Hey. Sorry. Anyway, so then I solve for big Y. It gives me this. These pieces need to be dealt with separately. This one, if we complete the square in the denominator, it gives me an s plus 3 squared plus 4, which then evidently we're going to get sines and cosines shifted by e to the minus 3t. And so then I just, I did 2 times s plus 3 here. That subtracts 6, which leaves me with 9. So I have 2 times 9 halves. The reason I'm pulling the 2 out is so that I realize I've got a 9 halves e to the minus 3t sine 2t from this, and this gives me a 2 times e to the minus 3t cosine t over here. And this one, I have to use the theorem. Notice whenever we're multiplying by e to the minus as, it multiplies by a u of t minus a when we go back to the time domain. So and I also, when I have a term like this, you could expect this to be matched over here. That's what the theorem says. So e to the minus 3 t minus pi times sine of 3 times t minus pi, like that. We did work other problems where we had a unit step function, right? And those are uglier. Because why? Because then when you take the Laplace transform of like a unit step function, you pick up 1 over s multiplying the e to the minus as, and then when you divide the other side by the characteristic equation, you've got like 1 over a cubic, right? Which is more challenging. I decided rather than to give you one of those, I would just give you a cubic inverse transform problem separately. So that's what I did here. So here I'm asking you to find the inverse transform of this. And so first order of business is to factor the denominator, namely s squared times s minus 4. That gives us this partial fractions decomposition, which works out to apparently a equals to 2, b equals to 3, c equals to 1 when you do the math, which brings us to this. And then we use the theorem. So the inverse transform of 1 over s minus 4 is e to the 4t. This is a 2. This transforms to, hey, what? Wait, what?
Wait, how do you get e to the 14 minus 3?
Moogly moogly. This transforms to 3t. What's that? How did I get this?
Yeah.
Oh, that's because notice that we have this multiplying over here, so we have to take e to the 4t evaluated at t minus 3. This inverse transforms to 2. This inverse transforms to t, so I have to replace the t with t minus 3, 3t, which replaces with 3 minus t. Words. Sorry. So I gave you a choose your own adventure route here, right? So the one route was to try to decide whether or not this vector field was conservative. The thing is, if you calculate if you check the closed condition on this vector field, right? If you calculate the y derivative of the x part and the x derivative of the y part, you would have found out that those are equal. So it appears it could be the case that it's conservative. However, if you saw through my plot, if you saw through my subterfuge here, you'd have seen this for what it is, which is this is 2x, 2y plus the gradient of the angle function example. So it's this plus that. Well, we talked about this. This thing integrates around the circle to give you 2 pi. This, on the other hand, is in fact the gradient of x squared plus y squared. That integrates to 0 around the circle. So this piece actually is conservative, but the other piece is not, because it integrates to 2 pi. If it was conservative, it would have to integrate to 0, but it does not, so it's not conservative. Yeah. That was a challenge question, and then this is the, one of these usual plug in the general power series, work out the recurrence relation, and then you study it, and you study it some more, and you tilt your head and squint, and eventually some patterns pop out at you, and then you put those together, and voila, there you go, answer. So, yeah. So I would say, if I were you, what I would recommend would be work back through the tests. If you guys need me to, I can post blank tests. Would that be helpful? Would that be helpful? I'll try to do that. I need to post blank tests in physics too. They wanted it there too. And then, of course, the other thing is just go back and, try to sort through the missions, right? What did we do? Do you guys have any questions about mission 5?